Snell's law. In this lesson, we're talking about refraction, the index of refraction, Snell's law, and then finding the critical angle using Snell's law. Refraction. Refraction occurs when waves speed up or slow down. Light rays change speed when they go from one medium to the other. So for instance, as we go from air to plastic, and then from plastic back to air, you can see our light changes direction. As the light changes speed, it changes direction, which causes the image to become distorted, as we can see in these pictures here. You can see the lines on the outside, right there and there, and then you can see the image created through refraction of the glass. How much the light speeds up or slows down in the new medium depends on the difference in the medium's n values. N represents the medium's index of refraction, which is the ratio of the speed of light in a vacuum to the speed of light in that medium. A bigger difference will result in a larger change in speed. So if you're going to go from an n equals 1 to an n equals 1.5, that's going to be less of a distortion than if you go from an n equals 1 to an n equals 2.5. So that's going to create a bigger difference. Our equation for index of refraction is n equals c over v, with n equaling the ratio of the speed of light in a vacuum to the speed of light in that particular medium. Snell's law. We can calculate the angle of refraction using Snell's law. Snell's law is n1 sine theta 1 equals n2 sine theta 2. Number 1 is going to represent the incident or first medium, and number 2 is going to represent the refracted or second medium. So this is going to be n equals 2 over here, and this one's going to be n equals 1 over here. Check your understanding. Light is shown underwater onto the plane surface of flint glass at an angle of incidence of 45 degrees. What is the angle of reflection off the flint glass? Does the refracted ray bend towards or away from the normal? And what is the angle of refraction in the flint glass? So I want you to pause the video, try the question, and then we'll take it up. Okay, so first thing we need to do is we need to draw what's going on. So that's going to be our barrier. Underneath here, we're going to have the water, and we're going to have the glass up here. Now, the index of refraction of the glass is 1.63, and the water is 1.33. Now, we know we're shining a light this way at an angle of 45 degrees. That's going to be our normal. And we need to know whether our ray is going to bend towards or away to help finish up our drawing here. Well, since we're going from a fast or a faster medium of water, n equals 1.33, to a slower medium, n equals 1.63, we know that we're going to bend towards the normal just a little bit. So I'm just going to draw it like that. Now, this is going to be our angle of refraction, otherwise known as our angle 2. This one's going to be our angle of incidence, otherwise known as 1. And we know this one is 45 degrees. We don't know what the angle of refraction is. So A says, what is the angle of reflection of light off the flint glass? Because we know we're going to get some partial reflection. So we know when it hits, it's going to bounce off this way as well. And what's the angle it's going to make when it bounces off? Well, the angle of incidence equals the angle of reflection. So the angle of reflection, so little r, is going to equal to 45 degrees. B, does the refracted ray bend towards or away from the normal? It's going to go towards the normal because we're going from a fast to slow. So it's going to slow down and go towards the normal. That's our definition. And C, what is the angle of refraction in the flint glass? Theta capital R. So we're going to write out our formula. We're going to say that n1 sine theta 1 equals n2 sine theta 2. n1 is going to be 1.33 sine 45 equals n2, which is 1.63 sine theta. So we need a little bit more room. So we're going to put it up here, and we're going to simplify. So we're going to divide both sides by 1.63. So we're going to be left with sine theta refraction equals 1.33 sine 45 divided by 1.63. And then we're going to simplify. We're going to say sine theta refraction is going to equal to, on your calculator, you do 1.33 times sine 45. You get an answer. You divide that answer by 1.63, and you get 0.577. Now, that isn't our answer. We're looking for the actual angle. To find that angle, you need to take the inverse of sine. So theta r is going to equal to sine minus 1, 0.577. So on your calculator, you're going to find the button that says inverse sine, or sine negative 1. You're going to put a bracket around it. You're going to put 0.577, and your answer becomes 35.2 degrees. And that's our final answer. Now, we can use sine's law to find the critical angle. The critical angle is the angle of incidence that creates an angle of refraction of 90 degrees. And the critical angle is always a number between two substances. So in this case, between water and air. To create a critical angle, you need to be going from a slow to a fast medium. If you're not, it's not going to work. Now, what do we say here? Well, the critical angle is the angle of incidence, that's the scale right there, that creates an angle of refraction of 90 degrees. So you can see how that's 90 degrees right there. It doesn't actually go into the second medium. We can calculate the critical angle using Snell's law. Remember, that's our Snell's law right there. we're going to replace theta 1 with theta critical and theta 2 with theta refraction. When we do that, we get n1 sine theta critical, because we were saying that the angle of incidence, or theta 1, equals the angle critical in these situations, equals n2 sine theta r, because in this case, theta 2 is going to be the angle of refraction, because theta 2 is going to equal to the angle of refraction. We know that the critical angle produces an angle of refraction of 90 degrees. That's what we're told in our definition. So we can replace theta 2, or theta r, with 90 degrees. Sine 90 equals 1, which simplifies our equation even further. So to break it down even further, we're going to say that, remember, n2 equals sine theta r. We're told that theta r is going to equal to 90 degrees. So we're going to say n2 equals sine 90. Sine 90 equals 1. So on the right-hand side of the equation, we're left with n2 times 1. On the left-hand side, it's still n1 sine theta critical. And like I said previously, for there to be a critical angle, you must be going from a slow to fast medium. Otherwise, it's not going to work. Check your understanding. Calculate the critical angle for the crown glass to air boundary to 1 decimal point. So pause the video, try the question, and then we'll take it up. Okay, so first up, let's draw our situation. So we know we're going from the glass to the air. We're told that the n for air is 1, and the n for glass is 1.52. This is going to be area 1, and that's going to be area 2. We're going to have a normal line right there, and we're going to have a ray that hits the plane right at that normal. Now in this spot here, we're going to call this the angle critical, and we know when we hit the angle critical, we get an angle of refraction of 90 degrees. So we got our situation all drawn out. So let's write out our equation. n1 sine theta 1 equals n2 sine theta 2. Now we're going to replace some of our variables. n1 is still n1. We're going to call angle of incidence now the angle critical. n2 is n2, and sine theta refraction. n1 is 1.52 sine angle critical, that's what we're looking for. n2 is 1 sine, and we know the angle of refraction is 90 degrees. Now the entire right-hand side is 1, because sine 90 is equal to 1. 1 times 1 is 1. So the right-hand side of the equation is 1. 1.52 sine angle critical. Now we're going to isolate sine angle critical by doing 1 divided by 1.52. And then we're going to find angle critical by taking the inverse sine, 1 divided by 1.52. Now to solve this with your calculator, you do inverse sine, bracket, 1 divided by 1.52 on your calculator, and bracket, and to 1 decimal place, you get an answer of 41.1 degrees. And that's our final answer. So to create an angle of refraction of 90 degrees, we need to have an angle of incidence of 41.1 degrees. That is our critical angle. Calculate the critical angle for the diamond air boundary to 1 decimal place. Okay, so we've gone through the steps a few times. Now we're just going to do a little faster. We know we're going to go from diamond, n equals 2.42, that's 1, and 2 is going to be air, which is 1. We're going to go some angle like that, and we're going to get a refracted ray of 90 degrees. So n1 sine angle 1 equals n2 sine theta 2. n1 sine angle critical equals n2 sine angle refraction. n1 we're told is 2.42. Sine angle critical equals 1 times sine 90. We know the right side is going to equal to 1. 2.42 sine theta critical. We're going to isolate sine angle critical. Equals 1 divided by 2.42. We're going to isolate the angle. So we're going to say theta critical is going to equal to sine negative 1, 1 divided by 2.42. And we're going to get an answer to 1 decimal place of 24.4 degrees. Now I said you need to be going from a slow to fast medium, so what I want you to do on your calculator right now is try the other way. See if you're trying to go from air to diamond. So on your calculator, you're going to put in sine negative 1, bracket 2.42, divided by 1, and bracket, and see what you get. If you ever get that on a question, you either know that it can't be done, or you did something wrong. And that concludes our lesson on Snell's law.